Welcome everybody to our next video in our series on probability and statistics. I, as always, am Dr. Lathram, and today we'll be talking about the negative binomial family of distributions. Now, for those of you who have seen our previous videos on the binomial family of distributions, this setup should look pretty familiar. So we start out with a collection of independent single experiments, and for a particular experiment, we have two possible outcomes. We either have a success or we have a failure. We'll assume that the probability of success on a single experiment is going to be p. And the random variable that we're going to be interested in is the number of trials in which this must occur before we have r successes. So now to contrast this with our binomial distribution, in our binomial distribution setting, we were interested in the number of successes that we had in n trials. Here, we're interested in having a fixed number of successes, r, and we're wondering how many trials it will take before we achieve that rth success. So in order to simplify the discussion, we'll begin with the simplest case where we take r to be 1. Now, for our case, r is equal to 1, we can really view the experiment with a really nice tree model. And so what it would look like is the following. So from our initial branch, we either have a success or a failure. We have a success with a probability p. We have a failure of 1 minus p. So now we're looking for a success. So when we hit the success on the first trial, we're done. But if we hit a failure, now we branch again. And again, with our branching, we either have a success or we have a failure. And so the probability of success is again p. Probability of failure is 1 minus p. So for y to be 1, so to have our first success on our first trial, we just have a probability of p. For y equal to 2, we go down one branch of failure and then down a branch of success. And so that'll give us a probability of 1 minus p times p. For y is equal to 3, now we have to branch twice down failure. So we have a 1 minus p times a 1 minus p, and then we branch to success, which is going to give us a p. For y equal to 4, we go 3 branches of failure and then 1 branch of success. And so if we continue this pattern, we can see that the probability that y is going to be equal to n is going to be 1 minus p to the n minus 1. So we've got n minus 1 branching failures. And then finally we get our one success to give us a probability of 1 minus p to the n minus 1 times p. And so now let's look at the PDF for this experiment. So we claim that the function f from the positive integer into the real numbers defined by f of y is equal to 1 minus p to the y minus 1 times p, where p is a value between 0 and 1. We claim that that is going to be a probability density function. So what we need to do is just check that it satisfies the requirements. So the fact that it's greater than or equal to 0 is pretty obvious. P is going to be between 0 and 1. So 1 minus p is between 0 and 1. You raise that to a positive exponent, and it's going to be, again, positive. P is positive. So everything in our PDF is positive. So sure enough, that condition is satisfied. But now we have to check the sum over all positive integers. And so if we write out our sum, we get the sum from 1 to infinity of 1 minus p to the y minus 1 times p. Well, we can factor that p out. We can pull that out to the front. And now in this sum, from 1 up to infinity of 1 minus p to the y minus 1, that's actually going to be a geometric series. So if you look back and think about your geometric series from Calc 2, you'll remember that we're able to sum that series for the ratio in between 0 and 1, and that's going to be 1 over 1 minus p. So when we're multiplying that by p, then that denominator just simplifies down to p. We have p on top, p on the bottom, and sure enough, that gives us a sum of 1. And so everything is positive. We've checked that the probability of the entire sample space is 1. And so our third axiom for our probability distributions is kind of automatically satisfied. And so we can sure enough say that yes, this does give us a probability density function. And so this really does bring us to our family of distributions. So this family is actually called the geometric family of distributions. Makes sense because we use the geometric series to sum everything together. And so if we have a random variable y, it is said to have a geometric probability distribution with a parameter p if and only if we can write the PDF as f of y equal to p times 1 minus p to the y minus 1, where y is going to be a positive integer. We kind of denote that, so we denote it with this notation, so y, the little tilde symbol, and then GEOP, GEO standing for the geometric family, and p being the designated parameter for that particular family. So now let's come back to our more general problem where we had not one success, but we wanted r successes. So let's take a look and see if we can tackle that problem. So we want our rth success to occur on the yth trial. And so if we kind of look at the sequence of outcomes, we've got this sequence of outcomes, observation number 1, observation sub 2, observation sub 3, all the way out to observation sub y minus 1. Now our rth success comes on the last trial, so we've got a success for the last entry in our observation. So the sequence of observations, O1 up to O sub y minus 1, we know that contains r minus 1 successes, and if we want, and so therefore y minus r failures. Now, we really don't care all that much where the r minus 1 successes are scattered in that y minus 1 trials. What really matters is that we are able to determine the number of ways that we can scatter those r minus 1 successes in the y minus 1 trials. And that is given by, of course, our binomial coefficients. So we've got y minus 1, choose r minus 1 is just exactly that number of ways of choosing r minus 1 positions in y minus 1 spots. Now the probability of our sequence, O sub 1, O sub 2, all the way up to O sub y minus 1, and then our last observation of a success, well, the probability of that sequence contains r successes and y minus r failures. And so that means we have a probability for that particular sequence of just being p to the r times 1 minus p to the y minus r. Now, from what we just done, we know the number of ways, so that we know the number of sequences that can occur, and we know the probability is going to be the same for each sequence, and so we can put these things together to find the probability of obtaining the rth success on the yth trial is given by y minus 1 choose r minus 1 times p to the r 1 minus p to the y minus r. So now, of course, this seems like a pretty good derivation. See, everything seems pretty solid, but we should always ask ourselves, is this really a probability density function? And so things that we need to check, first of all, is it going to be positive? Well, our binomial coefficients are positive. P is going to be a real number between 0 and 1, so 1 minus p and p are both positive. And so if we raise each one of those to powers, they're going to be positive. So that p of y or f of y is going to be greater than or equal to 0. That one is taken care of. And so what we really need to check then is that the probability of our sample space is actually 1. So that may take a little bit of doing, but let's see if we can tackle that. And so what we'll need, let's take a flashback back to our Calc 2 days. And so if we recall that for a real number r, and if we have the absolute value of x less than 1, then we can do a binomial expansion of a function. So if we look at the binomial expansion of 1 plus x raised to the s power, that's going to be the sum from k equals 0 up to infinity of s choose k x to the k. Now, this s, we had to extend the definition of our binomial coefficients back then to compensate for the fact that s might not be an integer anymore. And so we changed that to be defined as s choose k, where s choose k is going to be s times s minus 1 times s minus 2 all the way down to s minus k minus 1. All of that over k factorial, and that will be defined for k greater than or equal to 1, and of course for s choose 0, so that's consistent with everything else, s choose 0 is 1. And this is how we were able to get a power series expansion for the square root of 1 plus x. So the square root of 1 plus x was just going to be the sum from 0 to infinity of 1/2 choose k x to the k. Now if we look at the expansion of that, we get 1 plus 1/2 x minus 1/8 x squared plus blah 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 blah. So we are able to extend that and get an infinite series. Now these binomial coefficients, if we write out a few of them, we actually see that they obey this pattern. This 1/2 choose k is going to be minus 1 to the k, and then 1 times 3 times 5 times 7 all the way up to 2k minus 3, all of that divided by 2 to the kth power over k factorial. Now, if that's may have been a while since you've gone back and looked at your binomial expansions, but it's probably not a bad thing to go back and review. So if you want to stop the video, go back and review those, I'd say that's a pretty good idea. So now let's see if we can maybe rewrite what we will have as our PDF to maybe take advantage of these binomial expansions. And so we start off with our sum from r up to infinity of y minus 1 choose r minus 1 times 1 minus p to the y minus r. So if we do a change of summation and we let j equal to y minus r, then we can rewrite our summation to be from 0 up to infinity of j plus r minus 1 choose r minus 1, and then 1 minus p to the j. So now let's take a look at this honest to goodness binomial coefficient that we have here. And so if we write out its definition, now j is an integer, r is an integer, so this is our usual definition for our binomial coefficients. So if we just write that out, we've got j plus r minus 1 factorial over j factorial times r minus 1 factorial. And so kind of taking these last r minus 1 factorial over on the end, we'll kind of group those together. We cancel with an r minus 1 factorial in the denominator to give us j plus r minus 1 all the way down to r. And so what we can do, let's move the r to the front of that sum. And so kind of the pattern in our numerator, we've got r plus j minus 1, r plus j minus 2, r plus j minus 3, all the way down to r plus 0. And all of that over j factorial. So now in that in that numerator, we've really got a total of, so if we look at how many j's we're subtracting, so we've got 0, 1, 2, 3, all the way up to j minus 1. So we've got a total of j terms. And so if we pull out a negative 1 from each and every one of those terms, we end up with a negative 1 to the jth power times minus r minus j plus 1 minus r minus j plus 2 all the way down to minus r. And so if we kind of factor out the negative from the j plus 1, the negative from the j plus 2, we get an expression that looks like minus r minus j minus 1, minus r minus j minus 2, minus r minus j minus 3, all the way down to minus r minus 1, and then finally minus r. Well, now that is something that does match what our generalized binomial coefficients look like. It ends up being minus 1 to the jth power times minus r choose j. And so if we look back at our summation from r up to infinity, y minus 1 choose r minus 1, 1 minus p to the y minus r, if we make that substitution with our change of index, now we're summing from 0 to infinity, and our binomial coefficients looks like minus r choose j, and then minus 1 to the j times 1 minus p to the j. Well, that is our binomial expansion for 1 minus p raised to the minus r power. So this does match our expression whenever s is equal to minus r. And so if we plug this into what we had for our PDF, we factored out that p to the r. That comes out in the front. We know that our summation now is 1 over 1 minus p, that raised to the rth power. So simplifying that denominator, we just have p to the r in the denominator. Well, p to the r in the numerator, p to the r in the denominator, multiply them together, sure enough, we get 1. And so after that little bit of work, we get that the sum over our entire sample space, sure enough, is 1. And so yes, that does give us a probability density function. Again, the third axiom is kind of taken care of for us. And so yes, we have just developed a new family of distributions. In fact, that new family is the negative binomial family of distributions. So we've got a random variable y is said to have a negative binomial distribution with the parameters r as a positive integer and p, a real number between 0 and 1. If and only if we can write the PDF of y as a function with a domain r plus 1, r plus 2 into the real numbers, such that f of y is going to be y minus 1 choose r minus 1 and 1 minus p to the y minus r times p to the r. So the notation that we have to say that y has a negative binomial distribution is this y tilde nb, and then we write our parameters, our first parameter r and our second parameter p. So r is the number of successes that we're looking for. P is the probability of success on a single trial. Now, just to put this into context with what we did, the geometric family of distributions is actually kind of a subfamily of our negative binomial family. That it's a special case of the negative binomial family. If we take the special case where r is 1, then negative binomial 1p is the same as the geometric family with parameter p. So now later on we know we're going to want to find the mean and the variance, the standard deviation for these new distributions. And so the easiest way to do that is, of course, to look at the moment generating function. So let's see if we can derive the moment generating function. So going back to the definition, we've got m sub y for our moment generating function is just the expected value of e to the ty. Well, if we just take e to the ty, multiply it by our PDF, then we get an expression that looks like this. So then we do the same kind of trick as we did before. We do a change of index so that we let j equal to y minus r. So we get this new summation starting with our index starting from 0 up to infinity. The p to the r, the e to the rt has no dependence on j whatsoever, so let's pull that out to the front, and leaving us with this expression. Now everything to the jth power we can combine together to give us this expression, and then we use our trick that we just derived. This r plus j minus 1, choose r minus 1, is our generalized binomial coefficient, minus r, choose j, times minus 1 to the j. Well, what this actually gives us is, again, a binomial expansion of 1 minus, now x becomes 1 minus p times e to the t, and our power becomes, again, just as before, minus r. And so for our moment generating function, we end up with pe to the t divided by 1 minus p times e to the t, and all of that raised to the rth power. So now let's look at the mean and the variance. So if we assume that y has a negative binomial distribution with parameters r and p, then we claim that the expected value for y is just r over p, and the variance is given by 1 minus p times r over p squared. So how are we going to come up with that? Well, of course, use what we just did in our moment generating function. So if we take our moment generating function and we take the first derivative of that, we get this expression. Now, this expression is a simplified expression. What you would need is to go back and look at your quotient rule to take the derivative, and so I'll kind of leave that as an exercise to the viewer to go back and take the derivative, see if you can simplify everything and get down to this expression. But then we take this expression and plug in t equal to 0, do a little algebra, and sure enough, this simplifies to r over p. And of course, for the variance, we look at the second moment by taking the second derivative. So once again, this is a simplified expression. I'll leave it to you to successfully navigate the differential calculus to get you that expression. We take that expression, plug in t equal to 0, and we end up with r times r plus 1 minus p over p squared. For the definition of the variance now, it's the second moment minus the square of the first moment. And so plugging in the values that we've got r times r plus 1 minus p over p squared minus r squared over p squared. So we do some algebra, simplify that, and sure enough, we end up with our desired expression of r times 1 minus p over p squared. And so with this, we've kind of gotten through pretty much all of the details around the negative binomial family of distributions. We've looked at the geometric family as being a special case of the negative binomial family, and so now looks like we're probably ready to work a few problems with our negative binomial distributions. So hopefully you've enjoyed this video. It's gotten some good information out of it, and I look forward to seeing you all next time.